Hello to viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about high temperature heat pumps. So let's dive deep into it. Why the heck do we need high temperature heat pumps? Well, reality is that high temperature water, aka generally temperature of water which is above 100 degrees Celsius, and you're like, okay, how can water be above 100 degrees Celsius? Pressure. You increase pressure high enough, you can get it to be still be water as high as 200 degrees Celsius. So that is normal, and high temperature water is the backbone of all our industry. Like, if you think boiler is a normal thing, like who needs it now? No, everybody needs it. As in, go to your nearest industrial sector, just randomly put your finger into any building and most likely it will have a boiler. Like, it is important, and it is so important that it must meet two criteria. First, it has to be cheap, as in like running it cannot be expensive, because again, everything is built on top of it. If it's expensive, everything else also becomes prohibitively expensive. And then it has to be available, meaning it cannot be optional. It has to be like, I need it, it is there. It's almost like electricity. So that is there. Now, most people have sense of hot water in terms of domestic hot water. Now, generally, if it's said that if you have children and all that, babies specifically, do not have your hot water more than 35 degrees Celsius and adult 40 degrees Celsius. That's the safe upper limit zone, so to say. 50, 60 degrees Celsius hot water can give you first, second or third degree burns. And anything above that, you're danger. Yeah, and you could be dead. So that is there. However, the moment you go into industry, they start at 70 degrees Celsius, meaning at that point in time, any accident with hot water pipes will not hurt an individual, it shift delete the individual. So let that be like, it is serious thing, it is dangerous, and it can easily cross 200 degrees Celsius. So at that point in time, it does not burn, it removes the flesh from the bones. So that is there. And to give you a context, what sort of industry we are talking about, food and beverages, anything basically have that microbes. You generally do not want your food to be basically in this red zone basically, where food poisoning bacteria can live. And ideally you want to be below 5 degrees Celsius or above 60 degrees Celsius. You do not want to be in this red zone. So we generally heat things up above 60 degrees Celsius or 85 degrees, be it your orange juice, be it your milk, a lot of things, be it beer. So it is a very important step in packed food and beverages. Like, I'm pretty sure I do not have to explain the importance of milk. Like, if that puppy goes, we did. So very important, pasteurization. And be mindful, there is a step above that, which is sterilization. That is even higher. So that is there. Now we come to pharmaceutical. Definitely important, puppy. 121 to 134 degrees Celsius, because they sterilize the hell out of every single utensil, every single chamber, everything that is in the chain of pharmaceutical has to be sterilized with very, almost like a madness level of brutality, in order to make sure that you do not make a medicine that makes people sick. So, because again, especially medication that goes inside the body through basically injection, those things can inject anything bad into you, because again, they are bypassing your first layer of defense, which is your skin. So they have to go through very strict sterilization process. So pharmaceutical takes it very seriously, and lot of hot water and hot pressure. Then you come to petrochemical. That's a different ballgame. At that point in time, it's like, yo, lol. So petrochemical can easily go to 400 degrees Celsius. To give you a context, a lot of people smoke hydrogen and they're like, yeah, hydrogen, future energy. How the heck do you think we get hydrogen? We take methane, CH4, be it from biogas, be it from natural gas, and we cook it with steam of ludicrously high temperature, 400 to 600 or maybe 800 degrees Celsius. That gives you basically what we call a steam reforming. And again, that's one thing, if whole nation's hydrogen output comes from that generally, and there are other places also where you need steam reforming, and these are generally the highest temperature of water that is used, because above this you reach power plant. Basically below power plant, this is the highest temperature that is being consumed, so to say. And many other industry, this is the range. Like, if you can cross above 100 degrees Celsius, you can do stuff. 150 degrees Celsius, you can do a lot of stuff. 200 degrees Celsius, now only few things you cannot do. 500 degrees Celsius, you're done. At that, like, generally when you are talking about petrochemical industry, it's cheaper to just spend some amount of the fuel. So it does not make sense for them to, like, try to do optimization. But for other places, it does make sense to remove this puppy, because this puppy consumes gas, oil, whatever you feed into it, like there is no tomorrow. These are hungry puppies, so to say. So many industry uses that. So It's an important problem. So what the hell is this heat pump? Well, it's just your air condition. So a closed loop of working gas. Now, generally it is a gas, and we generally call it a refrigerant. What it could be methane, it could be propane, it could be butane, it could be CO2, it could be ammonia. So those sort of things. And what it does, this loop does, is basically utilizing the principle of phase change. It tricks heat into it, as in it takes heat from one place and dump it into another. It does not create cold. Let that be very clear. It does not create cold. There is no such thing as cold. All it simply means is there is less heat. And what this sort of phase change does is basically takes heat from one place and throws it another place. Now, how can you do that? Because again, fans cannot do that, and even technically coolers also does not do that. They just phase change water, and you end up with higher humidity in your room. What this puppy does is utilizes boiling. Basically, they have a refrigerant that boils generally at lower temperature, generally at a temperature that you want. So, for example, if you want cool, you will want something that boils a very low temperature, as in like, let's say, -5 degrees Celsius. So what happens if this liquid gets into your room? It will boil. But what does boiling means? Boiling simply means consuming energy. If you have boiled milk on a stove, what does that mean? That simply means stove is dumping energy into the milk it consuming it, and then changing phase. So that's what's happening here. Boiling water, same thing. So, and yes, water can be used as a refrigerant if the temperature requirement is suitable for that. So you generally boil things. Now here's the deal. Boiling things generally gives you, oh sorry, I'm pointing about this. Boiling means you are consuming energy and you get into what we call low pressure, low temperature, vapor. That vapor goes into your compressor. Now, compressor in this scenario is a mechanical compressor. Now, it could be rotary compressor, it could be piston compressor, it could be scroll compressor, but generally it's a mechanical device that is, you're not doing any reaction to it. You're just like compressing it. So at that point in time, you go from low pressure vapor to high pressure, high temperature vapor. At that point in time, you go into what we call condenser. Condenser blows air through you. Now here's this air is a higher temperature. Your indoor temperature was like, let's say 30 degrees Celsius. Outdoor would be 50 degrees Celsius. At that point in time, you're blowing 50 degrees Celsius. But here's because you have created high pressure and temperature, it is hotter than the outside ambient. Meaning if you put a thermometer here, it could easily be 55 or 60 or even 70 degrees Celsius. At that point in time, it dumps the heat outside. It condenses. Now it's a liquid. Because it's a liquid and in high pressure, you send it to what we call a metering device. Now, metering device is just a valve that allows it to expand in a controlled manner. Now, modern systems have even controllable valves. Basically, it controls the throttle. So that goes there, and tada, inside your room, it expands. It evaporates, consumes energy. The cycle repeats. There is no consumption of refrigerant. So it does work. All it needs is a two heat exchanger. We call it one condenser, one evaporator. They are the same thing. They could literally look the same, especially if it's a liquid system, it would look exactly the same. And they have a metering device and you have a compressor. So all this is normal. This is what you have in your refrigerator. This is what you have in your basically air source water heater. This is normal. This is common. Now what is deal? This is a complicated system. How do we measure whether it's working or not? Because it's a pump that is pumping heat. Same way a water pump is dependent on water pressure. Here it's dependent on temperature. So we simplify it and measure it by COP, coefficient of performance. For example, lift. Here the lift is basically what is the T delta you want to create between indoor and outdoor. So for example, if outdoor is very hot, 50 degrees Celsius, and you want indoor to be very cold, let's say 10 degrees Celsius, your compressor is gonna poop itself. But if it's, let's say, outdoor is not that hot, 35 degrees Celsius, indoor you only want 25 degrees, that's a 10 degree delta T. Your AC is like, I got this, I can do that. So coefficient of performance is basically how much energy you put in, as in like your compressor, and how much heat was moved into the condenser side of it. Then you take that and basically subtract this part to this part, and you will know how much energy was taken from the expander side, as in the evaporator. And heating side, basically what if you want to use it as a heating system? You are extracting heat from somewhere and dumping it, you get 1 plus. In cooling, you get 1 minus, because again, the compressor heat itself, the energy that compressor itself consumed will be dumped on the outside. So you do lose that in the cooling side. Heating, awesome. Heating generally is 1 COP plus. So if a COP system they are saying is 5 in both directions, it simply means you are getting 4 unit of cooling and 5 unit of heating. So coefficient of performance generally works that way. And again, 2 is bare minimum. If you are below 2, it's not that good. 3, really good. 5, 6, damn. 7, 8 is generally you cannot touch 7, 8 unless you are consuming something. For example, if you are running a data center and they need 7, 8 COP of refrigeration, they generally have a cooling tower, which is basically an open desert cooler. They are basically boiling water away in order to dump enough heat to achieve that sort of high COP. So 2, okay. 3, 4, good. 4, really awesome. 5, it does not make sense to use anything else. Like if you are touching 4 or 5 COP, let me put it this way. It is so much energy in terms of heat you are making. You cannot get that much heat if you are burning fuel. Like, why? Because again, burning fuel gives you energy. Heat pump moves it from somewhere. So for example, let's just say you have a scenario where let's just say you have a substation, right? Let's say you have a massive substation and next to it there is a small industrial plant that needs very high hot water. A substation, it has a lot of electrical equipment that creates a lot of waste heat, like transformers, battery charging stations, SCADA systems, a lot of waste heat. You collect all of that. That's waste heat. They have to dump it. You collected it. You dumped it into your system. Tada, you get hot water. If you have 5 COP, it is so much that you cannot consume the fuel and get more energy out of it. It would be better to use that fuel, generate electricity, run a heat pump, you still would be efficient. But again, that generally happens above 4. It does not happen below 4. 2, yeah, it's not that effective. 2 is just effective as in like, yeah, it would be better to consume less electricity. 3 is like, yeah, it would be stupid to run a resistive heater. 4 is like, yeah, stop. At that point in time, stop. There is no discussion at this point. 5, yeah, you're stupid to do anything else or even think of anything else. So that's the measurement of efficiency. 2, good. 3, really good. 4, 5, awesome. Now here's the deal. We are talking about lift. It's almost like a water pump. So generally each system has a lift capacity. As in generally it can only create a delta of 30 degree or 40 degrees Celsius. And here's the deal. Can you create more than that? Yes, of course. But penalty is your COP will go down. So instead of getting good COP of 3, you may go down to as low as 1.5, meaning you are consuming 1 kilowatt of electricity on your compressor and you're only getting 500 watts of cooling. Not effective. So that's why we do not want lift to be very high. But here's the deal. We are talking about very high temperature. Ambient could be hot. Even in India, it could be very hot. Let's say 60 degrees Celsius. But it's only 60 degrees Celsius. You need 110 degrees Celsius water. That's not enough, so to say. So at that point in time, you link multiple cycle of it, what we call cascading refrigeration. Basically, you have one refrigerant that is taking care of one section and one temperature lift, and you have second refrigerant that is creating second temperature lift. So this way you get the luxury of fine-tuning a system. Basically, what is the best refrigerant, best compressor, best everything for this lift. Basically, let's say lifting in Western places, minus 20 degrees Celsius heat to, let's say, 40 degrees Celsius. 40 is a bit too much. Let's say minus 20 to 20. Okay, that's all you are doing. Minus 20 to 20, 40 degree T delta you are creating. Okay, what is the best refrigerant for that? Okay, let's just say it comes out to be propane. You're like, okay, propane is awesome for that. You use propane at that point. What is the best compressor for propane? Because again, different refrigerant requires different compressors. Some compressors are high flow rate. Some compressors are high pressure. Some compressors are both high pressure and high flow. So you have to fine tune it. So you get one cycle that is like from minus 20 degrees Celsius to 20 degrees Celsius. Then you can put COT. CO2 could be like, hey, 20 degrees is like, I can easily lift this to 20 to 70 degrees Celsius. That can be done. And you're like, oh, yeah, delta becomes a bit different as, different refrigerant. You can do that. So that's the whole point of it. Basically, you create 2 loops, fine-tune it for each of their lift, and tada, you get very good COP. You cannot do, like, especially if it's a very large T delta, as in like, let's just say 60, 80, or maybe 100 degrees Celsius delta, you cannot achieve this with one refrigeration system. During the pandemic, you must have heard of the part that vaccines require a lot of effort in order to safe keep, and normal refrigeration does not cut it. How do you do that? Same thing. There are a lot of what we call very low temperature refrigerator. They are exactly the same thing. They have one cycle that is a normal refrigerator, just more capacity, but it's a normal refrigerator. It brings the temperature to a certain point. Then there is a second refrigerator that is running, dumping energy into that first loop, tada, dropping the temperature. Now, how many loops you can do? Generally, 2 is optimum. 3 you can do. Again, sometimes you do require very low temperature. Like let's just say you want minus 150 degrees Celsius. Yeah, you need to have 3 system. 4 is also done. But again, the more add you do, the more inefficient system, because yes, you will reach the temperature, but COP will become 0.5. So again, if you need that temperature, you need that temperature at the end. But if you're like, do we really need that much? It's like, that sort of point. So 2, optimum. 3 is like pushing it. And again, generally for economic reasons, we generally do not consider heat pump logical if it starts to reach 3 or 4. 2, awesome. Like 1, reasonably, it's unlikely that you can pull off. Even in Indian heat, you can pull off everything in 1 loop. But 2, we good. In India, if you have 2, cascade system, hot water, we can easily give you 4 to 5 COP or maybe even 6 COP in peak summer. At that point in time, it's like, yeah, it's idiotic to do anything else. And in winter, it could go down, but it will go down only to like what Europeans are like, the best case scenario at minus 20 degrees Celsius is like, 2 COP. We'll be like, yeah, we are at like 3.5. So you can do that. CO2 and ammonia, they are commonly used in 1 loop and another loop. That gives you like very good cascading effect. You want a lot of range, temperature range. This does that. And be mindful, this exact same philosophy works in both ways, meaning if you want to lift the temperature or you want to deplete, depress the temperature, same thing happens. You want a, minus 70 degree for antibiotics or RNA vaccines or something like that. They require very low temperature. Yeah, same thing. So that's the cascading part. You will never ever, most likely, will hear us in this thing, the end. It will always be, this is 1 loop, this is 2nd loop. That's how we get very high temperature. And again, if you try to do it with single one, lift has to be very low, or if you make the lift very high, COP will go down at that point in time. What's the point? So how does this work? Is it in real use? Well, here's the heat pump cannot work as a heater if there is no place where it's leaching heat from. So if you're like, what happens if outside heat, like let's say outside is completely cold, it's completely frozen over, what happens? Well, you have a 1 kilowatt heater. If that's your compressor power, you still have that. That's like a 100% efficient heater. Not that wise, because again, if all you're getting is 100% efficient, use a heating element. If you're spending so much money for refrigeration, evaporator and condenser, it must be more than 100. So that's the key part. You need a heat source. So your source matters. For example, you're like, hey, I need bonkers high temperature. Let's say India has a lot of pharmaceutical industry and they're like, bro, we need 120 degrees Celsius water. All I have to say, look up, put solar collectors, enjoy. So at that point in time, we do not have to worry. But again, other things could also happen. Let's say you are in Finland and you're like, hey, I need hot water. It's like, ooh, how close you are to the sea. Sea is the best heat source at that point in time. Not air. Again, it's very cold. Sun, you barely see them. So heat source matters. And as long as you can boil the refrigerant, that's the point of it, you can extract heat. So generally, the most optimum scenarios we have, like optimum as in COP wise, let that be very clear. You can make a system that works from very low. COP is low enough, it does not make sense. That's why generally at minus 20 degrees C is the, this is how far humanity has reached. And again, where the hell humans live, which is below minus 20 degrees Celsius for an extended period. Once in a while, or Antarctica and all that, that's a different thing. But I'm like, majority of humans do not live below minus 20 for long duration. Unless you are in Canada. Does Canada go below minus 20 degrees C for long duration? So in those sort of scenarios, you're going to get 2 or even 3. Some designs are really that good. They are almost pushing 3 COP at minus 20. I'm like, I'm scared what will happen if you try that in Indian winter. It will be like, boom, 6 COP. And a lot of Arctic cold places, they are realizing sea has seawater. Seawater, even if it's only 3 degrees Celsius, it is bonkers source of heat. Why? Because you have bonkers amount of it. And not to mention, water has ludicrously high heat capacity, meaning dropping that 1 degree Celsius water to 0 degrees Celsius water, it will take insane amount of energy. And especially because if you have so much flow, yeah, good luck. Like, it's almost like an infinite source. Yeah, of course, because you are trying to lift so much, trying to do that in one jump would be unwise because your COP will go down. But it can be done. It as a source of heat, it's good, it's done. UK is also trying that. So sea and rivers, as long as there is liquid and as long as the liquid is not almost at freezing point, you good. If it's like liquid is like, especially sea, if it's 4 or 5 degrees Celsius, you good. Oh, and this is a man system that is in one European nation. I have linked the video down below where they are targeting 2 and in summer they get 4. So that is there. And the best scenario is basically using waste heat. That's the sweet spot. You're not supposed to take heat out of places where like it's not designed for. Like for example, let's imagine it this way. Let's say you are pasteurizing milk. You heat it up, but here's the deal. You have to cool it down also. At that point in time, that makes a complete loop, meaning you are heating and cooling at the same time. Heat pump in this scenario is perfect. It's optimum. Like, of course, you can't reach 100% free energy, where it's like, perfectly heating it up, perfectly cooling it down, but you can reduce the power consumption by 20%. And so, a lot of people have figured out that, hey, once we boil something, generally there is a stage where we have to cool it down, or you have an exhaust that has already cooled down. So what if you take that exhaust heat, dump it back into the circulation? Even if you are using a gas boiler, imagine a gas boiler that's feed stock, instead of coming at, let's say, 30 degrees Celsius ambient water, it's 80 degrees Celsius, and it only has to target for 120 degrees Celsius. It's much less fuel consumption. So that's the whole point. Waste heat, that's your sweet spot. We have to close the loop. The moment you close the loop, you can get 4 or 5 COP. That's easy. And that COP is like, yeah, do not try to do anything else. 2 COP, okay. 3 COP, good. 4 or 5, yeah, stop discussion. Stop discussion. Meaning it's almost like, oh, you have a data center and you want district heating. Bro, perfect couple for each other. 1 unit of electricity you dump it into the compressors, you can give you 5 units of electricity. Heat, sorry. 5 units of heat. It's perfect. And again, you can cascade it if you need very high temperature. So what can we expect in the future? Well, reality is, as fuel and energy is becoming, be mindful, this sort of heat cycle and all that, heat pump and all that, we have known this for 2 centuries. It's just that electricity was cheap, people were cheap, humans were cheap, human resources. Like, look into like early industrial revolution, how many people were just getting kaput. Like, this is like kaput, there was no ocean. So fuel and energy cost has gone up exponentially, and meaning at this point in time, if you are building a plant and if you are not the most energy efficient possible, there is a very serious risk that in few years you will go out of business, because fuel prices are going so high, and electricity prices are even higher because of AI data center. So fundamentally, we are in a scenario where this sort of heat pump, industrial heat pumps, will go from fancy technology show off to must have. And this could happen very quickly, from like 3 to 5 years kind of scenario. So that is there. And we have to do better at integration. I get it. Like, people are like, oh, but this plant was built in like, 1810 and we are still maintaining it. It's like, bro, you can retrofit it. It's not impossible. You can do it while keeping it partially open or even fully open. Like, there are things there. It's just that we are not prioritizing it enough. Where it's like, okay, think in complete integration. For example, this is a new sector in Delhi, India's capital. They are building a new industrial system to boost economics and yield output. Here's the deal. Imagine if this place was built and they're like, hey, what if we put a heating and cooling loop underground, as in like basically like district heating and cooling. So anybody who needs like, hey, we need cooling, dump your heat into the loop rather than ambient air, dump your heat into the loop. Anybody who needs hot water, most will leach the heat from that. So basically you are coupling heat and cooling, cycling the efficiency. So that is the best way to improve yield, reduce carbon footprint, reduce energy consumption, improve everything basically. It's like, why burn energy when you don't have to? This is the most ironic part. Like, I have to say that the biggest tragedy of Indian solar is like, we have not jumped into PVT yet. Like, imagine like Indian, there are a lot of hotels, big hotels, they consume a lot of hot water for like, washing all the clothes and all that. Imagine if they're like, hey, we have solar panels that also make hot water. And like, okay, but the hot water will not be as hot. Yeah, but it still would be 10 degree minimum 10 degree delta T. And here's the deal, that's raw, as in like, if you're not doing anything, you dump heat pump into it, you can get very high temperature. Like, you can get bonkersly high temperature. If ambient is 50 degrees Celsius, reaching 80 degrees Celsius water is like, bruh, 60, 70, 80. Done. One compressor stage is like, bro, I got this. CO2 is like, bro, I got this. Me good. So we can do that. Like, basically, it will give you electricity. That's the first part. It will give you heat. That's another part. That means GG ROI, as in your return on investment will happen much quickly, because a panel will produce more electricity if it's cooler, and you're getting heat, which you are using. So that is the one point. Meaning in summer, 4 and 5 COP is like, bro. And in India, cold is not that cold. Although hot is hot, but cold is not that cold. So 3 is achievable. This is the whole point. Basically, industrial sector have to realize that, again, thankfully they are in concentrated places, so it can be done. It's like same way district places are like, hey, district cooling. It's like, hey, industrial loopage, let's just call it industrial looping, where you have heating and cooling. So hey, we run a lot of air compressors that dumps a lot of heat. Cool, collect it. The equipment will last longer. You will collect the waste heat, dump it into some individual who needs that. It's like, hey, bro, we are pasteurizing water. Or paper industry. Ooh, those puppy consume steam like there is no tomorrow. So district and heating and cooling should be like, in a co-generation kind of scenario. It's like, hey, we have this powerful substation. It has so much waste heat. I'm pretty sure you can remove 1 or 2 boiler from the system just by the waste heat of one substation. And God help you if it's a big substation in India in summer. So that's the whole point. Basically, we have to change our mindset. This whole idea of like, what if we do nothing and like get something, or no. Like, we really need to close the loop. You'll be shocked how much energy we can save if we do the closed loop system. And again, let that be, it will happen. It's just that companies will willingly do it, or they will be forced to do it because they will be like, yeah, we can't afford burning fuel and electricity as we keep been doing. So, but this does require a little bit of foresight that only a government can do, where it's like, hey, please, like, lay down a foundation of a system where everybody can tap in and tap out thermal energy. It's like, I dump heat, I extract heat. If both can be balanced, awesome things can be done for very low cost. So this was my presentation on basically industrial heat pumps, high temperature industrial heat pumps. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.